Today we're going to take a look at the first part of section 9.2, which is multi-stage experiments. This might be the most interesting section of material that we cover this semester. It also might be the most challenging because it may be a little bit outside of some of the things that you've done or maybe at least delved this far into in some ideas of probability already before. The first thing I want to introduce you to is the idea of a tree diagram. You guys have done like factor trees before, right? This is kind of like that. A tree diagram is a sample space model where each outcome is designated by a separate branch. What you saw in 9.1 are what are called one-stage experiments. One-stage experiments are experiments that is over after one step, i.e. one set of branches. Okay, so this is the idea of I reached into the sock drawer and I pulled out one sock. I decided I was going to have a kid and I had one kid. I had a whole bucket of marbles and I pulled out one marble. That's a one-stage experiment. Two-stage experiments, which is what we're going to mostly be seeing happening in this lesson, are experiments that are over after two steps or two sets of branches. Now you'll notice that the lesson's title doesn't say two-stage experiments, it says multi-stage. So sometimes we're going to encounter experiments that have more than two stages, right? Like we're going to encounter a problem in this set where we have three children. Okay, so you reach in 3 times from the drawer, you pulled out 3 socks, you pulled out 3 crayons from the coloring box, whatever, okay? So we're going to be doing 3-stage, there's one where we're going to do a 4-stage one, I can't remember if it's in class or in your homework, but these are multi-stage experiments. Piece of information that's very valuable for our tree diagrams is the multiplication rule for tree diagrams. For all multi-stage experiments, the probability of an outcome along any path of a tree diagram is equal to the product of the probabilities along that path. There are some problems that you will do that I know you can do them because you can reason through them and think through how to do the mathematics, like the numerical part of it, without a tree diagram. But I want for you to show me tree diagrams on each step. Because if you were working with some of these content ideas, they wouldn't be as complicated. I get that. Okay, I get that. But your students in your classroom would not be able to reason at the same level that you can. They just can't, right? They don't have the experience that you do. And so them drawing a tree diagram is the most natural way, or at least one of the most natural ways that they would solve the problem. So we're going to practice tree diagrams. There's also some equivalent items that we'll do that are like tree diagrams. I'll mention it when we do it so you can see what I mean, where it's equivalent to doing a tree diagram, but it isn't actually a tree diagram. So there's a couple places where that comes up. Note, allow yourself space to do this. So if you're one of those people who skips problems when you don't know what to do with them, make sure you're skipping a good chunk of space when you do these problems, because when you go back and you fill that space in, it's going to fill up really quickly if you've got to have to do a tree diagram in that space. Okay? All right. You guys encountered mutually exclusive things last time. They were items that had nothing in common. People like to get that confused with this idea, which is independent events. Independent events are events in which the outcome of one event has no influence on the outcome of a second event. Okay, so an example of an independent event would be something like it rains today and it rains next week, next Tuesday or something like that. They're far enough apart, there's not a direct correlation that one is necessarily affecting the other. Or I roll a dice and I get a 2, or I flip a coin and I get a heads. No way, shape, or form affecting each other, right? But there are lots of events that do have a relationship that's not independent. They're dependent events, right? Like it very much might play into whether or not the weather might very much play into whether or not you decide to go out for a run. Now, you might be one of those people where it just doesn't matter and it really doesn't affect you. But most of us, there's a threshold, right? Like if it's pouring, I mean, we're right in that category that says, nope, not me. But if it's sprinkling, some of you might be like, nope, not me. And some of you might be like, no, that's fine. Okay, so there are plenty of things that affect each other. All right, we have one more equation that we're going to add to our list of equations about probabilities. So if we have independent events and we want to know what's the probability of two events happening, right? So like the probability that I did roll a dice and get a 2 and flipped a coin and get a heads, and I want the probability of both those things happening and they're actually independent, then all I do is multiply each event's probabilities together. So in my example I just gave, there's a 1/6 chance that I'm going to roll a 2. There's a 1/2 chance I'm going to flip a heads. So it's 1/6 times 1/2. I just multiply those outcomes together. All right. Absolutely love this question. This question's a really good example of events that are not independent. It matters. So let's actually talk about what's going on here. We've got an executive committee. It has 10 members on the committee. 4 are women and 6 are men. And 3 of them are going to be selected at random to go to Hawaii. Evidently, it's not COVID, right? It's not going to work right now. You have to quarantine for 2 weeks if you get to Hawaii. I have an aunt that lives there. That's why she didn't get to come home this summer. Yeah. So let's flip over to the second page so you can see what the questions are that they're going to ask, because it will actually help determine how we draw our picture. It asks us questions based on the gender of the people. What is the probability that we select 3 women? What is this probability that we select at least 1 man? So yes, there are 10 different people. I do not need to draw 10 branches. Okay? I don't. Because the only thing that I'm sort of categorizing here is whether it's a man or a woman that's sort of falling into a category, right? That's the only thing that matters in the description. So when I draw my tree diagram, I can do it one of 2 ways. Let me just show you one of them. I'll erase it and I'll show you the other one. Most of the time, I draw mine from left to right. So I'm going to draw 2 branches out like this. Their branches, in my case, are going to say man and woman, or you could say male and female if you want, something like that. Okay? If you don't want to draw them like that, some people like to draw them top down. You can draw it right like that, and you can make your branches come like this, and you can branch out from below. Or down below. It doesn't matter. Okay, so I'm going to go back to what I had because that's the way I normally do mine, and it's probably works better on the spacing on my screen right now. So I have man and woman. Okay, so in the bucket right now, everybody's names are dumped into the bucket. And we reach in and we pick out one name. All right, so how likely is it that we pick out the name of a man? How many men are in the bucket? 6. How many names total are in the bucket? 10. There's a 6 out of 10 chance that we select a man's name. So what's the likelihood that we select a woman's name? 4 out of 10. Make sense? And notice, along this branch, they have to add up to the value 1. Every set of branches works like that. It's not unique to this problem. They will always, within a specific part of the tree, that specific set of branches has to add up to the number 1. Okay, so we're going to now go off of the man category. We pretend like we picked out the name of a man. We are going to draw name number 2. Again, I have options of men or women. But it's no longer 6/10 and 4/10. Because somebody's name's already been drawn. He's not going to go to Hawaii twice, so he doesn't get his name put back into the bucket, right? So there are now how many names in my bucket? 9. So I now have 9 as my denominator for each of my fractions along my branches. How many of the names are men's names? 5. Notice there's not 6 because along this branch I drew out the name of a man. How many names are women?
4.
The same 4 I had before. Okay, now if I go, if I go to the other half of my tree diagram, this tree diagram spot assumes that I drew the name out of a woman. So there are still 9 names in here, but they're not the same probabilities as the tree branches above. It's not 5/9 and 4/9. How many men's names are still in the bucket if I drew a woman's name out first? 6. And how many women's names are in the bucket? 3. Okay, so again, each set of trees, or each set of branches has to add up to 1. That would be a set of branches, okay? Okay, this would be taking 2 people to Hawaii, but we're supposed to take 3. So we're going to draw 1 more set of branches. Like that. All of them are going to have MW, right? Man, woman. Okay, but every branch location depends on what was done beforehand, okay? So none of these branches have any reason to believe that they're going to be equal to the other branches that you see. So we're going to start along the very top one. So on the top row, we've selected a man's name twice. So how many men's names are still left in the bucket? 4 out of how many? 8. And I still have the same 4 women because no one has been selected. But along the second branch, I've selected a man first and a woman second, right? Man and then woman. So along that branch, there's still 8 names in the basket because I already selected 2 of them. But how many are men? 5. And how many are women? 3. Now, interestingly enough, along this particular next branch, it's the same probabilities because now I've selected a woman and a man, which means I selected one of each gender. So I still have removed 1 person, so I still have that 5 over 8 for the men and the 3 over 8 for the women. Those do not look good. I'm so sorry. How about that? Score. Good job. Yeah, set it over to the side. All right, and our last branch down here at the bottom, we've selected 2 women. So how many women are left in my bucket? Or their names, not the people themselves. 2, right? 2 women's names, and there are still 6 men's names in the bucket. This is a completed tree diagram. Okay? Now, the reality is, if they only asked me what's the probability that all 3 selected are women, I wouldn't necessarily have to flesh out the whole tree diagram. But you're usually asked more than one question, which means you don't really get to shortcut the system and only do part of the tree diagram that you need. It doesn't usually work that way. So on our tree diagram, if I want to know the probability of selecting all women, it's asking me about this particular branch. Are you with me? And over here, we found that when we're working with a tree diagram along a specific branch of independent events, which these are independent now because I changed all the probabilities as I went along, I multiply along the branches of the tree diagram. So we're going to multiply 4 over 10, 3 over 9, and 2 over 8. So we have 4 over 9, 3 over 10. I didn't say that right at all. 4 over 10. Not that it really matters, but we'll do right. 4 over 10, 3 over 9, and 2 over 8. Okay, so this is multiplying fractions. We did this 2 chapters ago, right? We did. We did this back in chapter 6. You can simplify along the diagonals if you'd like. I think that will help us. So I'm going to do that. We've got 4 and 8 here. So that gives me a 2 in the denominator here, which is actually really friendly because that cancels the 2 that's in the numerator and the denominator there. So that's nice. In the middle, the 3 and the 9 itself, 3 divides by 3 and gives me 1. 9 divides by 3 and gives me 3. So I'm left with a 1 on top and a 30 on bottom. Not very likely, right? 1 out of 30 chance. Yeah, probably not going to happen. And mostly that's happening, of course, because there's more men's names in the bucket, right? Yeah. Now, on part B, it wants to know what's the probability that at least 1 man is selected. So let's actually look back at our tree diagram. What it's actually asking me for is every branch where I have at least 1 man selected. Well, that's this branch, and this one, 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 and this one. It's everything that I didn't already do, right? Every branch that was not already the red one along the bottom. So this is the probability of 1 minus selecting all women, because it's all of the other tree branches. So if you wanted to, yes, you could multiply along every single tree branch. That's 7 times of multiplication, and then you could add them all up. That's possible. Won't hurt anything, but it's a lot of work. It's a lot easier to just simply take 1 minus the 1 over 30 that we got from part A, and what will we end up with? 29 over 30. It is very likely that at least one man will be selected to go on the trip. Okay, we have problem for example number 2, and then we'll stop for today. Example number 2 is the case that I was talking about, or at least one of the cases I was talking about, where we're not going to draw a tree diagram, but we're going to do some equivalent work where you're going to see how it plays out. A box contains 5 slips of paper, numbered 4, 6, 7, 8, and 9. A player reaches into the box and draws out 2 slips of paper and adds them up. If the sum is even, the player wins. If the sum is odd, the player loses. So we're going to write down all the possible things that could happen. In other words, I could draw a 4 and a 6. Notice I'm not replacing it, so I can't draw a 4 and then a 4. That's not a possibility. I draw 2 at the same time. So I could draw a 4 and a 6. I could draw a 4 and a 7. I could draw a 4 and an 8. Or I could draw a 4 and a 9. Those are the only combinations of things with 4s in them, right? Aren't any other possibilities. So maybe I don't draw a 4 at all, but I still draw a 6. Well, I'm not going to do 6 and 4 because I already listed that possibility. But I could draw a 6 and a 7, or a 6 and an 8, or a 6 and a 9. Notice there's one fewer because I already took into account the 4, 6. So this is now all the pies of drawing 4s and 6s and combining them with things. So maybe I don't. Maybe I draw a 7 and an 8, or a 7 and a 9, or an 8 and a 9. So they're not in branches, but I'm still listing out all the possibilities. Does that make sense? And what I want to know is which of these are actually going to be even values. So let's go through, and you can write down, turn the volume off. You can write out the actual values if you want. I'm just going to highlight them. 4 plus 6 is even. 4 plus 7 is not. 4 plus 8 is even. 4 plus 9 is not. 6 plus 7 is not. 6 plus 8 is. 6 plus 9 is not. 7 plus 8 is not. 7 plus 9 is. And 8 plus 9 is not. Okay, so you're just going to go through, add them up, identify how many of them you have, give you even numbers. And the reason I'm choosing even is because it says if the sum is even, the player wins. So how many of them have even answers? Well, how many of them are highlighted in yellow or orange? 4. Out of how many possibilities total? 10. And then 4 out of 10 can reduce to 2 out of 5. B, does the probability change if the two numbers are multiplied? So the question is asking us to do the same thing, but to identify which ones are even if they're multiplied together. Multiplication is a little bit easier to do because the multiplication will be even if either number is even. So it's always going to be even if I multiply by 4. It's always going to be even if I multiply by 6. And it's always going to be even if I multiply by 8. That's just about everything. The only one that's not even is the 7 times 9, if I'm doing it that way. Notice I didn't go back and change these to say multiplication. I just used the list that I had. But I'm thinking of them as multiplication now. So the answer, of course, is yes, they changes, right? Now there are 9 of them that are even when I multiply out of 10. Instead of 2 out of 5. Any questions on that one? Do you understand how I'm still showing the work that I need? Notice I don't have any probabilities listed like I'd had probabilities listed along my tree diagram. I can get away with that because each of them are equally likely. I'm just drawing 2 numbers at random out of the basket, right? The reason that that didn't happen, over here was because there was an uneven number of men and women, and every time I reached back in, after I drew one out, it changed. I only reached in one time here, so that's what's happening. All right, we will pick back up on example 3 next time. Have a wonderful weekend. Remember, go ahead and get those redos done if at all possible this weekend for the first time since you don't have any homework.